Okay, back. So we said the equivalence relation has a relationship with three properties. One, A is related to A for any A. We call this reflexivity. Next, if A related to B, then B is related to A. We call it symmetry. If A is related to B, B is related to C, then A is related to C. And we call this transitivity. So an example of an equivalence relationship would be rhyming on a set of all words. A rhymes with B, then B will rhyme with A. However, something that's not an equivalence relationship is taller than. First of all, John is not taller than himself. And also, but however, even though we have transitivity, A is taller than B, John is taller than Jim, Jim is taller than Joe. Therefore, Alan, or the first person, John is taller than Joe. I think that's the first person. Alan's taller than Bob, Bob's taller than Chris, then Alan is taller than Chris. However, even though Alan's taller than Bob, Bob's not taller than Alan. So we don't have a symmetry here. We do have transitivity though. We fail at reflexivity. So this is not an equivalence relation on the set of all people. So big property, we can see that if we had all these three properties and we looked at the universe, every element in the universe, because of one, is going to fall into its own congruence class, or a congruence class. It has to be some set. So we know it's partition. So we know that it's union of all the equivalence classes. Ooh, I forgot to define equivalence class. Okay, we look at the set, all the things that are related to each other. For example, Tim rhymes with Chris. No, this is Tim. Philip rhymes with Billup. Rhymes with Willip. Rhymes with Tillip. And we call the equivalence class containing Philip as R Philip. This means it has anything that rhymes with Philip. Anything that's related to Philip is in this class. That's an equivalence class. So look at this guy. So each guy is guaranteed to be in an equivalence class by ARA. It's related to itself. Therefore, it falls under an equivalence class RA for any object A. So going back to the integer modulo example, R2, equivalence class relating 2, is equal to the equivalence class containing 4, because that's just the set of all even numbers. They're the same equivalence class. But this does not even equal the equivalence class containing 1. So R2, or R6 even, equal R2, equal R4, equal just the evens. When we partition the even integers. So look, we're guaranteed each one is in something. You're also guaranteed that if they're related, and because transitivity and symmetry, we ensure that they do not overlap. Because if they did overlap, if one thing was related to another, then by symmetry and transitivity, it would actually be the same equivalence relation. So this guarantees that we can have an equivalence, if we break something up into equivalence classes, that these sets are disjoint. So let's do even and odds. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So even better, a congruence class mod n. We can look at the numbers mod up to n. Look at the first n plus 1, n plus 2, up to n plus n, 3n, so forth, 2n plus 1. And I can say these columns, anything that when you mod by n has a remainder of 1 is its own equivalence class. In other words, I'm saying x minus y, x is related to y, if and only if x minus y mod n, x is identically y mod n. So 1 and n plus 1 are identically the same when you mod by n. Same thing with 2 and n plus 2, and n plus 2n plus 3, or 2n plus 2, and so forth. 3's, the 4's, the n is related to n plus n, 3n, so forth. So I have broken up using this equivalent relation of x related to y, if only if x is related to y, x identically y mod n. And I have shown, and I have broken up the universe of all positive integers into equivalence classes. Very good. So the other one, now we're going to go into Lagrange's theorem. Before I do that, I'm going to prove to you one equivalence relation. Consider the equivalence relation for let H be a subgroup, and say, okay, we say y, a, x is related to y, and where x and y are in the universe of the group we're dealing with. So H subgroup of G, x and y in G. If and only if y inverse of x is in G. So this means that, so we can prove, it's obvious this is an equivalence relationship because it fulfills the three properties. One, y inverse for any x, or any a inverse a equals E. And identity is always in G. Oh, I'm sorry, I did not mean G, I mean H. So x is related to y for x and y in G, if and only if y inverse x is in H. A inverse A is equals E, and that's always in a subgroup, always entity in subgroup. So reflexivity holds. Secondly, we know y inverse x, suppose y inverse x is in H. Well, H is a subgroup, so therefore we invert this. So y inverse x, so y inverse of x inverse is in H. But y inverse x inverse is simply x inverse y inverse, or x inverse y, which is in H. So this says that x, so we know y is related to x. Now I know that, or we know x is related to y, now we know y is related to x. So symmetry holds. We also know, lastly, from symmetry, so transitivity, I know, suppose x is related to y, and y related to z. Okay, x related to y, y related to z. So by definition, y inverse x is in H, and z inverse, yeah, that means z inverse y is in H. Okay, I want to show x related to z, which says z inverse x is in H. Right, okay, y inverse x, z inverse y. I want to show z inverse x is in H. How do I show this? Very simple. I take, the kids are here, z inverse x. I simply do, because I know these are in H. H is closed under addition, under the multiplication. So therefore I know z inverse y from this guy is in H, and I multiply, I know this is in H, so multiply y inverse x. By associativity, I close parentheses here, is in H. So z inverse x is in H, meaning that we have the third property, transitivity. Okay, I have to close soon, my kids are here, I teach Lagrange's theorem later. Thank you.